Hello, welcome back. Today we're going to be differentiating exponential functions, okay? We've done a little bit of this before, and we know that the derivative of e to the x is e to the x. And that was because it was a very unique function where its gradient was actually its value. So at this point here, y, the location, is the same as y dash, or I could rewrite that as y equals dy dx. Now we know that one. We might have even done some simpler e to the, if we had y equals e to the 2x, I could say that dy dx equals 2e to the 2x, because it's the derivative of that pops out the front. Now today we're just going to extend it to any function, really. So if I go e to the any function of x there, that derivative falls down the front. So just quick example, y equals e to the, put it to a quadratic. That means dy dx equals, the derivative of this is 2x, and that exponential function remains the same. Let's do a proof for that, and then we'll get into some questions. Okay, let's take y equals e to the f of x. The way I can prove this is by using the chain rule and substitution. Okay, so I'm going to say, well, I'm going to let this thing here be equal to u. So I'm going to say u equals f of x. I'm also going to say now that if that's u, y equals e to the u. I can then differentiate both. Du dx equals f dash x, and dy dx, well, that's dy du, I should say. Dy du equals e to the u, because it's just itself. And then I can use the good old chain rule, and I can say, well, dy dx equals dy du times du dx, because they will cancel out there. Okie equals dy du is this, e to the u, and du dx is this. Substituting back in for u, e to the f of x times f dash x, or if I want to write it with it out the front, e to the f dash x, e to the f of x. So the derivative is just spat out the front. And that is essentially it. Examples might be get a little bit tricky though, so let's do a few of these. Right, e to the y equals e to the x plus e to the minus x. The derivative of that is 1. Well, I know this one anyway, so that's just y equals e to the x. The derivative of minus x is minus 1, so that comes out at minus e to the minus x. That guy stays the same. That's y dash. Y equals 5e to the 4x minus 3. Derivative of this is 4. y equals 5 times 4 is 20e 4x minus 3. y dash. I'm going to start writing dy dx because I keep forgetting my y dash. Y equals e to the 2 minus x on 2. dy dx, the derivative of this guy here is minus a half. E to the 2 minus x on 2. That exponential function stays the same. D, I've got y equals, I'm going to write it all in with powers instead of surds. E, well, that's a half, so it's x on 2 plus e to the x on 2 but on the bottom, so e to the negative x on 2. From here we're very similar to the first one. 2y dx equals a half e to the x on 2 minus e to the minus x on 2 on 2. And sorry, that's because the derivative of that is minus a half. So that comes here. Alrighty, next. Use the chain rule to differentiate. Well, don't know if I actually want to use. We are using the chain rule. Okay, they want us to set it out the long way, but we are using the chain rule is what we did in the proof. So if we've done it in the proof, I think we're fine to just go and use it. Y equals e to the 1 minus x squared. Now the derivative of that, 1 minus x squared, well, this is kind of the chain rule, isn't it? If f of x equals 1 minus x squared, f dash x would be equal to, what's that, minus 2x. So dy dx equals minus 2x, e 1 minus x squared. Exact same. This guy here, we're combining a couple of different rules. This will be like chain in chain or something. I don't know what you call it. I don't like calling things the chain rule. For me, the chain rule, this is just what I think is this. Oh, is this. dy dx equals dy du onto u dx, which is like, makes a chain, doesn't it? 2 on 3 by 3 on 4, this kind of thing. Boom, boom. Anyway, I digress. Let's do this one. Y dy dx equals 4 comes down. E to the 2x minus 3 to the 3. And now the derivative of the inside is going to spit out. The derivative of minus 3 is just 3. The derivative of e to the 2x is 2e to the 2x. Now when I did this one, I did, well, that's f of x to the n, isn't it? D by dx of f of x to the n equals n fx n minus 1 f dash x. Sorry, a bit messy. Okay, and that equals 2, 4, 8 e to the 2x, just writing this last term at the front, e to the 2x minus 3 to the 3. Voila. Next, right, what have I got? Find the derivatives of these functions, then factor the derivative and write down all the stationary points. So we're just going to do the exact same thing that we did with integration. We're going to have to sketch these, whole bunch of different stuff. But Let's just start practicing. This is setting us up for integration, by the way, yeah. Y equals x cubed e to the x. Now, do I have to write out, it's a product rule. Do I have to write out the u's and the, we'll do it once. U equals x cubed, u dash equals 3x squared, v equals e to the x, v dash equals e to the x, because it's just itself. That means that dy dx, I'm going to stop using y dash. It's sloppy. Dy dx equals u dv plus v du. Alright. Now this factoring out, factor the derivative and write down all the stationary points. This is really nice, and this is what we want to, I want you to be able to see how to factorize this. If I look at it, I can see an e to the x, so I could factor out equals, go back to blue, equals e to the x cubed plus 3x squared. Now that's fine, but there's also an x squared. You could solve it off this, but I'm going to look for the highest factor, okay? It'll still work the other way. But I'm going to take out that x squared e to the x. Outside of x plus 3. Cool. Stationary points. I've got stationary points when dy dx equals 0. So 0 equals, make a bit more room here, 0 equals x squared e to the x plus 3. Here I get one only when x is 0. Because e to the x can never be 0. E to the x here can never be 0. That's because it's just never crosses that line. It's never 0. So I've got x equals 0 on that one, and on this one I've got x equals minus 3. Now it said find the stationary points, so I have to find them as points, not just the x values, but also the y values or coordinate of the point. Okay, so I'm subbing in up top to get my location out. X is 0, y equals 0 times e to the 0, 0 times e to the 0. Doing a lot of work in here, just because it's a video. Okay, probably skip a bit. X equals 3, y equals minus 3 cubed by e to the 3 equals e to the 3 on 3 cubed is 27 on 27. So I've got one stationary point at 0, 0 and one at minus 3 minus e cubed on 27, which is just some decimal. And we could check that by chucking it in GeoGebra or something like that. Or Desmos. I'll let you guys do that though. Last one, okay? Here, product rule. What do we got? I'm not going to write the u's and the v's this time. We'll just do it. Alright. Y equals hold 1. Hold the second one. And derive the other. We get 1 plus hold 1. And derive the other. The 5 will pop down the bottom. The exponential guy will remain the same. That's dy dx. Set that to 0. Stationary points when dy dx equals 0. 0 equals e to the 5x minus 2 plus x, 5x, e to the 5x minus 2. Take out, what can I take out here? Just the e to the 5x minus 2 outside of 1 plus 5x. Now this exponential function here can never be equal to 0. So this guy's only going to have one stationary point. So no solutions there. No solutions there. And here, I'm going to go to x is minus a fifth. I'll have to sub that y, x is minus a fifth in, and I'm going to get minus a fifth e to the 5 times minus a fifth minus 2, and that's all in the exponent, all that I've written there, which is, this might come out nice, minus a fifth e to the minus 1 minus 2 is minus 3 equals minus 1 on 5e3. So that's not bad. Okay, what kind of stationary point is it? Or are these? I don't know at this point. I could do double derivative, I could test either side, and again I could sketch these, couldn't I? I won't do it in GeoGebra today. I'll leave that for you guys to do. Okay, that's it for today, maybe. See you guys soon.